All right, let's get started. Welcome back, everybody. So today we want to start talking about cache designs. Before that, let's finish that example quickly, and then we're gonna come back to the cache design. Here's the code. Take a screenshot, guys. Okay, I'm gonna. Good, yeah. It's QJ3AOH27. All right. So let's go back. All right. So if you remember, we were discussing out of order execution. We kind of give you this kind of kind of step-by-step approach that we have. This thing called ROB here. We have this thing called reservation station here. And then we have a bunch of things that to kind of keep track of what is ready and what is not ready. We have functional units, register alias table, and some pools, free pools and registers for kind of keeping track of things. And then essentially we kind of have different steps, right? We have fetch, decode, dispatch, issue, fire, complete, retire, and so on and so forth. And we kind of go step by step for this example. And then kind of the notation we used was was the clock cycle. This are the events that is happening during the clock cycle. The fetch and decode, we said that is essentially exactly the same thing. Yeah, question. Yeah, I'm gonna come back to the code. So fetch and decode. And then basically at some point we're going to start doing the renaming, and then for the renaming, basically what we need to do is that for the source register, we just go to the table and copy that register, physical register, and for the destination register, we need to create a new destination register. That's why we kind of change this what used to be P2 to P6, and what this was used to be P4 to P7. So kind of like we are updating this table here. We got rid of those registers from the free pool, and then we move on to the next instruction. So we decode in section cycle 2, and then that's where we kind of do what we call a dispatch. The dispatch was this kind of activity where we kind of reserve a row in the reservation station, and we reserve a row in ROB. And then we kind of populate the different columns in ROB and reservation station based on the data. The important thing was in reservation station specifically, the important thing was this readiness of registers. And then basically for the source registers, we need to go to this table and see whether the source registers are ready or not. And we put yes or no here. The destination register was the important one, where you essentially needs to, as the moment that you put the destination register into your reservation station, you need to mark the register as not ready anymore, right? So that's the important things to remember. Then another thing that we do is that we also reserve a line in the ROB, and then we put relevant things in the ROB as well. And then we do all of these things in kind of in stride of 2, because this is a 2-issue superscalar processor. If it was 4, then we do 4. If it was just 1, that was like a scalar processor, which was you doing it one by one. So we kind of continue doing this, and we rename for this the other 2, and then we kind of update the rat table and then put it there. Then we're going to go to the issue stage here. So this is in the new cycle. This is cycle 4. So issue is actually happening during every cycle. The reason that we didn't have any issue prior to this clock cycle was there was nothing to issue. But at this cycle, there is something to issue, and how the issue logic basically works. So you can think about issue logic as basically this thing that goes through this table as a for loop. So start always from here and check all of these rows and see if there is a row that the ready bits are equal to 1. So all the source registers are 1, and the functional unit is also ready. So in this particular case, for example, if you look into this row here, you will see that the source register 1 is ready, source register 2 is ready, it requires the functional unit too. And if you actually look into the functional unit, you will see that the functional unit is also ready. So source is already, functional units already, then that means that this instruction can be issued. Okay. So basically what happens at this point is that we kind of feed this into our functional units. So we can actually remove this from this table and then feed it into our functional units. Okay. And what will happen is that you kind of change this readiness of this functional unit now back to no, because now there is one instruction that goes through the functional units. You can no longer issue another instruction that goes to the same functional unit at the same cycle. You can use other functional units, but you can not issue two instructions at the same functional unit at the same time, right? So I got rid of this and I make this not ready. Everything else kind of stays the same. Of course, this is a two issue processor, which means that I can essentially issue two instructions at the same time. So the issue logic basically goes through the table again. Check whether there's another instruction that we can do. So first of all, we see that these two instructions are not valid. So there's nothing to issue here or here. The only option would be potentially this one, but this one, as we can see, is that the source ready is not ready yet. So I cannot issue this instruction, right? So the only thing that I can issue is just one instruction at this particular clock cycle. Okay. I continue. This time I need to dispatch these two instructions. The bottom two instruction, the dispatch is actually the same thing that we described before. First of all, we start with OR. We put the OR in into this table. We put P8, we make P8 not ready, we put P5, we check whether P5 is yes or no, we put yes, we check P7, we see that it's no. There is no immediate in this particular instruction, and then functional units can be 1, and then the ROB is basically the same thing that we are putting here. Same thing for load, 1, load, P9, make P9 not ready, P0, yes, P0, yes. And immediates, in this case, we put it here. The functional unit for load can only be 2. So we put 2 here, we put ROB here. Okay, so it's kind of like, following the exact same algorithm that we discussed before. We continue. So in cycle 4, the issue basically, like, this load instruction was issued. And for example, in this particular example, I'm assuming that everything takes exactly 1 cycle. In your homework, for example, we made a difference. We make it a little bit different and said that your loads takes 2 cycles. For this example that I'm giving you here in the lecture, load takes only 1 cycle. So as a result, if I issue things in cycle 4, in cycle 5, the instruction will be completed, which means that basically the only thing that happens during the complete is that this instruction, which was that instruction that they issue, then the kind of the flag, the complete flag on the ROB becomes 1. And another important thing that happens is that, remember that my functional unit was not ready. Now it becomes ready because it no longer is inside that functional unit. So this also becomes yes. And another important thing that happens is the destination register, this P6 here, is now can be kind of like become ready, because now I have the value, right? For P6, I have the updated value. So I can actually use this value for the subsequent instructions, right? So for example, if you look at actually here, you see that, and then the next add instruction is actually waiting for that value. So the moment that the instruction is complete, now I can actually kind of forward this from the ROB to the reservation station, which means that now I can issue this add instruction, okay? So the important things that is happening here is that now I mark P6 ready, okay? And one thing that I'm not showing here is that I need to update this value here. I basically go through the reservation station and update that value from the ROB to the reservation station. This is exactly the same thing that we were doing for forwarding in our pipeline processor. Remember that we had the data in our ALU, and then we were forwarding that data from the, outside, the end of ALU or the beginning of the mem back into the ALU sources. This is exactly the same thing. So I'm forwarding this data into my reservation station. So I basically update that value as I'm doing this, okay? And then the big thing that happening here is that now this value is updated. I kind of showing it as boldface, and then I mark this as ready as well, okay? So this is all we can do in the complete stage. Remember that you cannot complete and retire in the same cycle. So I cannot say that, oh, okay, this is the head of ROB and it's completed, so I can retire it at the same cycle as well. Retire happens always at the next cycle after the complete. So you cannot do the same thing at the same cycle. So here, this is the only thing that was issued in the previous cycle. So that's why there's only one instruction that will be completed this cycle. So now let's talk about the issue. As I said, again, issue is this logic that goes through basically goes through this this table and check each line one by one. It first checks this first one and see that this is not valid, then checks this one and see yes, yes, and then functional unit 0 is also yes. So this is the first thing that we're going to issue. Can go to the next one and see yes, and then see no, so I cannot issue this one. Then goes to this one and see yes, yes, and 2, and then 2 is also yes. So I'm going to issue the add instruction and load instruction at the same time to my functional units. Of course, I need to make this functional units to not ready anymore, but I get rid of these 2 lines from my reservation station, okay? And then what will happen is that this is kind of like a continuous sequence of instruction. I'm not showing future instructions here, but you can imagine that, you know, the pipeline is always filled, right? So you fetch and decode the next 2 instruction, and then you push those into your reservation station and so on and so forth. I'm just showing a snapshot of 4 instructions in the pipeline. Well, of course, this is not always 4. There's always like a huge sequence of instructions in your pipeline. So we continue doing this. So now we go to the cycle 6. So we were at cycle 5, we'll be done with the issue. There's nothing else to do. We go to the cycle 6, and then the first thing that we need to do is retiring the instruction, checking whether there is retire. Remember this, the criteria for retiring was that the instruction has to be completed and has to be at the head of the ROB. In this case, this previous instruction was at the head of ROB and the complete was yes. So we're gonna add next cycle at this beginning of this retire cycle. Boom, I'm gonna get rid of that from the ROB, and then I'm gonna update my register file, and I'm going to update my memory and PC and anything else that needs to be updated. The important thing is here is that I'm gonna free the old register here. So if you remember, the old register was P2, so I'm gonna put back P2 into my free pool, okay? I'm freeing the old one, not the current one, because the current one is still in use, but the old one is now ready to be freed. So I put back P2 in my free pool, and then I'm going to continue. I also going to move my head of ROB 1 step down. Remember, I can kind of like retire 2 at the same time. So I'm going to check whether this instruction can also be retired. But since the complete is not arrived yet, I cannot retire this instruction. And I cannot retire anything beyond that because I only can retire things from the head of the ROB. So it doesn't matter whether, for example, this one was yes or not. I cannot retire this because I can only retire things in order, right? So this is it with the retire complete. Remember that we issued 2 instructions at the previous cycle. So I'm expecting to see 2 instructions to be completed at this cycle. This instruction will be completed. So I'm going to put yes here. I'm going to put yes here. I'm going to put yes here. These are the things that I'm going to change. And then as you can see, this is basically means that I can forward this back to here. So I'm going to update this. I'm going to make this yes as well. There's another instruction that needs to be completed, I believe. Yeah, this one also needs to be completed. I'm not sure why I'm not putting it here, but this one should be yes as well. This one should be yes as well. And then we move on from the complete stage. Then we go to the issue stage. Yeah, remember that these are yes. We go to the issue stage and we see that, okay, this one can be issued now because this has, you know, flipped from no to yes. So I'm going to issue this as well and get rid of this. And now it's time for C7. So here, this one is actually yes. And I can actually kind of technically can retire this, but since the head of the ROB is here, I cannot retire this instruction before this instruction. So this one has to wait. I have to retire this one first, but since this one has been issued in the previous cycle, I cannot retire it. I have to wait. So basically nothing really happens at this point. The only thing is that I retire one instruction, which is this one. So I put this one back into my free table. That's the only thing that happens here. So all of these things become complete at this stage. And then at the next cycle, I basically can retire two at the same time because both of them are ready. Both of them head off the ROB. Boom, boom. I'm going to retire two instructions and that's it. And as you can see, this is basically what we're going to have at cycle 8 onwards. So this is the new updated table. The head of the ROB would be here. And this would be our updated kind of, RAD table. This would be our updated free pool. Everything has to at some point become ready again, and then we're ready for the next set of instructions. As I said, this is not going to be like this. There is always like things that are not going to be ready because there is always instruction inside my pipeline. But as I said, I just showed you a small snapshot of this sequence of instructions. Yeah.
Why is the first two instructions not completed in C4?
C4. I just issued this here, right? So the question is why it's not completed in C4. So we issued this in C4, right? So we will complete it in C5. Right? What's the question?
Right. Fetch, rename, dispatch, and then decode.
No, fetch, decode, dispatch. Fetch, decode, rename, dispatch, and then issue. Any other questions? All right, so that's it with the instructions. You have your homework to also play with. I think the TA also had another example, so you'll have 3 examples to kind of go over this. Let us know if you have any questions. Okay. Any final questions about this example? We're good. Yeah.
Do we assume that the function unit only takes 1 cycle?
Say it again.
Do we assume that the function unit only takes 1 cycle?
The question is, do we assume that functional units takes 1 cycle to run? This is something that you will be given. So it depends on the architecture. For example, if you remember, I showed you some instructions might, some functional units, such as if it's like a floating unit, functional units, it might take 8 cycles. I don't know. For your homework, for example, we indicated that your load board takes 2. So this kind of things that I'm showing here is slightly different on that particular example. Right? Yeah.
Are the entries in the ROB actually deleting or just serious?
Yeah, the question is, are the instructions in the ROB deleted, or are you? So I mean, the simplest thing is just flipping 1 bit rather than really going and literally zeroing them out. I mean, for some security reasons, or if there is a context switch, then you have to really delete them. But in most cases, you just toggle the flip bit, the valid bit, and that's it. So if the valid bit is 0, it means that you can override. If the valid bit is 1, it means that you cannot override. By the way, this is a code for those of you who missed it. Any questions? Yeah. Yeah, QJ3AOH27.
Working.
Is Q as in Quentin, J as in Java, number 3, A as in alpha, O as in orange, H as in half, and 27.
Yeah, that's the
Are you sure that you're using the correct link? Everybody else is working. I don't know what's going on with this. I mean, you can take it at the end of the class. All right. So this is the out of order execution that we talked about. Just a quick recapping. In order to build an out of order processor, you need the dispatching and renaming. You need retiring and ROBs. You need scheduling and reservation station. And basically, you need this notion of functional units and complete. So these are kind of the new concepts that we introduced in order to achieve out of order execution. There are lots of questions that we didn't really go very deep into it. Some of it I'm going to quickly go over in the next few slides. Some of it we can read. The whole point of talking about out of order execution was to kind of show you a little bit of details on how this works. But if you want to really go deep into the out of order execution, two things that you're going to learn is you can either take the advanced marker architecture course CS 251, and then another course that I'm teaching on spring of this year, which is also on advanced computer architecture. There we're going to actually talk more about out of order execution. Here I wanted to kind of introduce you to the concept so that you kind of know what's the difference between in order and out of order. Okay. But let me talk quickly about some of the issues that we have observed in pipeline stages and see what is the equivalent of that in out of order execution. Okay. As I said, the goal is mostly just giving you some basic high level. I'll post a kind of optional read for you guys who are interested to learn more. And of course, if you want to kind of learn more about the implementation, in the honors section, we are implementing a full out of order processor. So for those of you who are interested, you can always check the specs of that project as well. Of course, you don't need to do it. So the few design choices. The first one is you might wonder whether we need a separate reservation station and separate ROB, or can we actually combine these two into one, what we call a centralized design, okay? And in fact, in many of the modern processors, some of the Intel and AMD versions, actually, there is this idea of centralized. So you can actually have a centralized RS and ROB, which is essentially there's just one giant ROB. That reservation station is essentially part of it. So in that case, then you don't need to kind of link the reservation station row with the ROB row. Forwarding becomes significantly easier, and so on and so forth. So many designs are actually using what we call a unified or centralized ROB or reservation station. In the class, we kind of define it as two separate things to make it more understandable. But in many high-end designs, these are actually the same thing. Okay. And then we can have separate queues for functional units, or we can have so basically we can have kind of like something like this, that we have functional units here, and then we can have one giant reservation station that is connected to all of them, or we can have kind of like something like this, that there is like a dedicated reservation station for each of these functional units. And then the code kind of based on which type of instruction this is kind of put things into their dedicated rows. So this is also another design choice of some of these systems. Okay. Another thing that you see variation is the way that we do renaming. The way that we describe it in the class is using the register alias table and physical registers. But there's also a very popular alternative solution, which we use basically tags instead of doing the renaming. And then essentially you kind of assign tags to each architectural register. And then you kind of like broadcast and move this tag around. So if you have heard about Tomasolow's algorithm, and this is a very famous algorithm, it's one of the first designs of out of order execution. And that one is not based on rats, it's based on moving the tags around. In principle, it's the same thing. We are basically changing the architectural registers, but instead of assigning a physical register to it, we assign a tag to it, and then we kind of move this tag around. Okay, so slightly different the way that you need to broadcast a tag and you need to implement this. At the high level, they're exactly the same thing. Since we are not really going to the details of the implementation, doesn't matter which one we are using. Another thing that you might wonder is that where we exactly store the operands. So when you're actually reading our physical register file and get these values, I told you that basically this goes into my reservation station, and then I'm kind of like putting these values here. And I also told you that when the instruction is complete, this is kind of forwarded back and update these values here inside the reservation station. So this is the kind of the idea that we go after. But an alternative idea here is that you don't really store things inside your reservation station. All you do is basically just adding muxes and do the forwarding. So if this is your functional unit and this is your ROB, okay, and this is your reservation station, what you can do is that once the functional unit is kind of completed, I kind of put this back into some form of a multiplexer and then mux the data inside my FUs. Instead of really going into the reservation station and update my reservation station, I just send a signal to do the forwarding, and then I forward it inside my functional units. The advantage of this is that you don't need to have the right registers, right? So you don't need to update your registers every time. The disadvantage of this is that the wiring becomes more complicated because now you need another mux and so on and so forth. Okay, so just the difference is that when I want to do the forwarding, do I do the forwarding inside the reservation station or do I do forwarding inside the functional unit? So these are the two different options that you can have. And then generally another kind of like, a more generic implementation decision is that I don't even kind of like update the older value inside my reservation station. I always keep things in my register file. And whenever I need to read something, I just go and read it from the register file. So basically it just populates the tags or populates the names without really populating the data. And the data always just directly from the register file goes into my functional unit, okay? So that's the alternative that we really have. So the real, reg read is really happening during the execution stage, during the functional unit stage, okay? So that's an alternative. But as I said, what we have discussed is that you write it to the reservation station, and then from the reservation station, you pass it to the functional units. This is, again, much more intuitive to understand rather than you just pass the names and then you read them from the register file. Yeah.
Updating the value.
That's a good question. So if you're really writing it into the reservation station, you're wasting a clock cycle. There are ways that you can do this. It's like the same idea of a half cycle. So you kind of from the complete you write and then you read in the second half cycle. There are ways that you can do this. You can write it faster. There are different ways to do it. But the simplest one is the half cycle. So another thing that actually I think some person asked in Campus Wire as well was when are really doing the forwarding? And as I describe it in the example, once the instruction is completed, we have the updated value, and at this point we kind of forward it back to the reservation station, right? So the forwarding really happens during the complete. The alternative option is that if you actually wait for the instruction to be retired, updated the register file, and then you can just easily read it from the register file, right? The difference between these two is one cycle difference. The advantage of this approach is that it makes things significantly simpler because all you need to do is just always reading from the register file. You don't need the muxes, you don't need the forwarding, you don't need to forward from reservations, ROB to reservation station, all those things. The downside of this is that you're wasting one cycle. So for very, very high-end processors, this is not any option. You always have to forward once the instruction is complete. But if you want to save on area and power and so on, that's one option that we can do. So for lower-end processors, that's what you might see in the design implementations. And then we kind of also casually talked about this, that what do we do in flush? Essentially, we flush things from the reservation station. We flush things from the ROB. We restore the RAT. So whatever we have flushed, we need to go back and put the old register back as the register. So that's an important thing that we need to do. We need to free the destination registers because these are flushed. So everything that we kind of used need to put back in the free pool. If it was now it's not ready, we made them again ready because we have flushed them. And then if there is any instruction within the functional unit that needs to be flushed, we need to also get rid of that and free the functional units as well. And then PC, of course, has to be updated if this is a control flow instruction, right? So essentially the flushing is exactly the opposite of all the things that we did during the actual execution. We need to go back and update our rats, update our free pool. We need to check our functional units. We need to check our reservation station. We need to check our ROV. So everything has to be kind of reversed, all right? But the good thing is that we kind of keep track of everything, so we can do this easily. So for kind of recovering and restoring, there are two kind of main things that we can do. So all of these things that I said, we can do one instruction at a time. We usually call this a log-based method, which we essentially said, okay, for every single instruction, I need to check whether my rat needs to be updated and restored back to the previous case, and so on and so forth. So essentially, if I have like all these instructions, I go one by one, flush this one, update everything, flush this one, update everything, flush this one, update everything, and so on. This is kind of like what we talked about in pipeline stages as well. An alternative scenario to this is what we call a checkpoint-based solution. So essentially, the checkpoint is like, for example, whenever I see a branch, I take a snapshot of all of my units, my reservation stations, my rat, and so on and so forth. And then I let everything to go. And if at some point I decided I need to flush, I don't need to go instruction by instruction. All I need to do is copying the checkpoint that I have back into my design. So if I have a copy of everything, if I have twice a copy of everything, not everything, but most of the things, then what I can do is that the moment I see that there is a branch and there might be potentially some flushing, I just take a snapshot of my system. I take a checkpoint of my system, copy it into the kind of like the reserved unit. Then I continue. And then if I decided I need to flush, then the flushing would be very, very faster, because I basically just go and copy what I had before back into my design. This is what we actually intuitively do in many, many systems, right? If I want to change anything, I first take a copy and then change it. Of course, the complexity of this is that I need to kind of have a replicate of my entire data path in some sense. So that means more area, more power, more complex wiring. But that makes the checkpointing significantly faster, because in paper, you can do it in one cycle, right? So your kind of penalty of misprediction becomes only one cycle, back into what we had in a pipeline, decoding the stages of branch prediction, okay? So this kind of approach is, again, this checkpointing approach is very common in high-end processors, because it gives you speed, okay? And the last thing I want to talk about is handling the hazards. So basically, if you really think about the hazards that we had, so first of all, we eliminate those false dependencies, the write after write and write after read. Those have been eliminated by using the renaming. So with renaming, we are just back into the old hazards that we have: the raw data hazard, the control hazard, and the structural hazards. The raw data hazard is essentially fixed by having this ready bits, right? So if you're using the destination register, you make the ready bit equal to 0. You only make the ready bit back to 1 when the data has been updated, right? So this ready bit is basically fixing the issue of raw data hazards in our design, and that's great. The control hazard, I just described how we fix the control hazards. We either use some form of log base or checkpoint base in order to kind of recover our system. And then if you have a structural hazard, which means that any of our units are full, then we're going to stall the processor. So we check the reservation station or ROBs or functional units. If either of these three are full, we're going to stall the processor and make sure that they are kind of emptied first, and then we're going to continue executing instructions. So we fix that by having this basic pack of all of these things. The interesting thing is that there will be a new hazard in out of order execution, and that's for memory dependency, okay? The interesting thing about memory dependency is that you're gonna have the same raw data hazard right after write data hazard, and right after read data hazards because of the memory. Why? Let me give you an example. So consider something like this, right? So I have store x1, 0, x2. I have a store x3, 0, x4, okay? And what is this? This basically says that I'm going to update the value of the address that is in X2. So the mem X2 gets the value of X1. So this first instruction says this, right? And the second instruction basically says that mem X4 gets X3, right? This is a classic story. And then you might think that, okay, this makes sense. There's no problem with this. But what if X2 and X4 are the same? If they're the same, you're basically writing this to the same address. And what are you writing to that address? You're writing X1 one time and you're writing X3 one time, right? And what should be the final value of that memory? The final value of this memory should be basically this, right? Should be whatever value that is stored in X3 should be the updated memory value of the memory. Because remember, we need to do things in order, okay? But if you look into this, you will see that our out of order execution machine does not understand the dependency between these two instructions, because this one, the first one is using X2 and X1 as their sources. So in our reservation station, we check X1 and X2 and say, okay, they are ready. And then the second instruction is X3 and X4. And they, again, they are different from X1 and X2. So we might actually, accidentally, actually run this second store first and then run the first store. And that can create lots of problems for us, okay? So this is what we call memory dependency, okay? And this thing that can actually happen for raw data hazards. So here I'm showing a write after write, but this could be a read after write if the second one is a load. Could be write after read and so on and so forth. So essentially, if you change the load and store to each other, the read and write will be switched, okay? So how do we fix them? And remember, renaming doesn't help because you're not renaming source registers. You are renaming destination registers, and you cannot rename memory addresses, right? So because these are content, these are not names, okay? So in order to fix that, we have this thing called load store queues, or LSQs, okay? The idea of the LSQ is that it basically acts similarly to the ROB. So whatever load or store you have, instead of really writing it to the memory, you first put them into this load store queue. And then this load store queue is basically issuing things in order, okay? And the beauty of this load store queue is that whenever we have a new memory access, we first go and check the load store queue and see if it exists there. If it exists there, we don't go to the memory, we read it from there. So we always guarantee that the most updated value of each of the memory lines is within that load store queue, okay? And so we only kind of remove the instruction, the load or store instruction from this load store queue whenever the instruction is retired, okay? So basically, during the complete, we write things to my load store queue, but once the instruction is retired, I'm going to get rid of that from the load store queue. So your load store queue is kind of like, looks something like this, basically. So the data in is basically coming from your functional units. You store the values, you put the addresses here, and then whenever we say that, okay, this instruction can be retired, then I'm going to write it to the data memory. Otherwise, I'm gonna basically check this and then put this data out if there is any sort of any sort of request that's coming from the processor. Okay, and this, by the way, fixed the issue of raw data hazards as well, because since I'm checking the load store queue whenever there is a request, and I always make sure that I write and the memory with in order retirements, I can always make sure that there is no raw data hazard, because I can never read before write, because the load store queue is similar to the ROB. It basically makes things in order. Okay, so essentially I'm always checking my load store queue, and then if there is any sort of stores that happens before loads, I always make sure that I do the forwarding from the load store queues. Okay, and then you can actually think about load store queue as part of your ROB in some sense. And again, I'm showing this as two separate units. but in reality, they can be all part of one giant centralized storage unit. Okay. So again, to kind of summarize, we have any load or store, instead of going directly to the memory, is going to kind of write themselves into this unit that we call load store use. We only write to the memory when the instruction is retired. In other words, we only write in memory in program order. Okay. And then if there is a subsequent load or store, the first thing that we check is this LSQ. If the data exists in that LSQ, we're going to forward it from the LSQ to the registers. Okay, we're not going to go through the memory and read that data. We're going to check the LSQ first and then get the data from there. And this way, we are always making sure that the most recent copy of the data exists in my LSQ. Yeah.
If instructions are retired in order, right, then why do we still need them?
So the question is, if the instructions retired in order, why still do we need this? Because of scenario like this, right? So if I have something like this, think about that. What happens in your reservation stations? I might actually issue this first, the second store first, and then this store, right? So it goes to it goes through my functional unit, and then it goes to my ROB, right? So now the next one comes, and then the next one wants to read. For example, like a load comes and load wants to read. If I put this if I read this from the memory instead of reading it from the ROB, then I'm going to have a problem, right? So that's why you read from the LSQ instead of reading from the memory direct. I mean, fixing this will not save you from that sort of problem. All right, so this is kind of it for out of order execution. We kind of go through lots of different things in a short period of time. The reason that I wanted to talk about this is that this is usually the only time that you know about out of order execution, and out of order execution is actually the most dominant type of architecture that exists in your systems. So almost more than 90% of all your processors in your cell phone, in your laptops, and your PCs, they're all out of order execution units. So in order, you very, very rarely see. You only see it in very, very tiny microcontrollers. Everything else that you see in your life, there's some form of out of order execution. So it's very important to know in principle how it works. There are lots of details in terms of implementation that we didn't have a chance to talk about. If you're interested, definitely read about them or take more courses. But just remember this kind of big idea of like renaming and moving things around and retiring and so on. So yeah.
Use something like a debugger, is that a simply result in a bunch of installs to make sure that it happens in order from your perspective?
If you have like a debugger at your software level. Yeah, so essentially, so the question is, if you have a debugger, what would happen in terms of out of order execution? So typically debuggers or any sort of like high level create some interrupts to your system, okay? So the interrupt basically kind of pause the execution of an instruction, jumps to somewhere else, and then run that, and then comes back and then execute the rest, okay? So this is typically what happens. But what you will see at the architectural stage is only things that have been retired. You will never see which instructions are completed. You will only see the retired instructions. So that's why there's a distinction between architectural stage and macro architectural stage. Macro architectural stage, the programmer does not have any idea about, okay? We don't know whether there is forwarding. We don't know whether there is stalls. We don't know any of that. The only thing that we do know is that I can read my X0 to X31. I can read my memory. I can read my PC. That's all things that I can see. But we're actually going to talk a little bit about interrupts later on in the class. Okay. So what's next? So let's actually kind of like take a step back and move on from the processor, and let's talk about memory a little bit, okay? And particularly, let's talk about memory hierarchy. So for the next few lectures this week and next week, I'm going to mostly talk about memory. So I'm going to talk about caches, various different things about caches. Then I'm going to talk about the main memory and virtual addressing, physical addressing, and those things. So I'm going to switch gear a little bit. We talk a lot about processors and make really, really fast. And in terms of timeline, we're around 2003, 2004 at the moment. And that's when we're gonna hit what we call hit the power wall. So we're gonna do all these optimization for out of order execution, checkpointing, etc., etc. And then our processor is going to get so bloated that it's going to generate lots of heat. And unfortunately, we can no longer add more features. Okay. And we kind of in some form of like, pause in terms of what we can do with the processor. Well, now let's kind of take a step back and think about memory a little bit. Let's make the memory also a little bit faster. And then later on, I'm going to come back to the processor and give you some idea how we make the processor even faster. Okay. So if you remember this, that we kind of early on started discussing this, I told you about we follow this one Newman model where essentially we have the CPU and memory as two separate things inside our system. So let's talk about this memory. And if you remember, we had this thing called memory wall. Essentially, this memory wall is this issue that over time, the speed of like increasing the memory performance didn't keep up with the speed of the processor. We kind of, during the golden age of computer architecture, we had around 60% per year improvement in the performance of CPUs. But since we couldn't do much on the memory except for the technology, the speed of increasing the speed of memory was around 7%. Okay. Which means that we kind of like this distance between these two grow and grow, as at some point really doesn't matter how fast your CPU works, you are always bounded by speed of the memory. If you need to bring lots of things from memory, doesn't matter how fast you can kind of like process this. The bottleneck becomes the memory, okay? And this event called the memory wall. Basically, the memory becomes the bottleneck of your system, okay? So how do we basically fix this this memory wall? And the fundamental problem is that unfortunately our technology dictates us that the memory can either be large or can be either fast. You cannot have fast and large memory. You can either have fast memories that they are very, very small, or you can have very, very large memories that are incredibly slow, okay? To give you some perspective, I showed this slide a long time ago. Let's revisit this one more time. The fastest memory that you can have are your flip-flops or registers that are within your processor. These are really fast. You can access them within 1 cycle in picosecond or nanosecond time range. But they are very, very expensive in terms of area. Tens of registers required for just storing 1 bit, okay? As a result, you cannot have like a gigantic register file. You can have maybe 32 registers, 128 registers, and so on and so forth, okay? One step, improvement of flip-flop or registers or what we call SRAMs. SRAMs or static RAMs are fairly fast. You can still access them within few cycles. And then you can access kind of like parallel access of multiple bits at the same time, which we call warp. But they are still expensive. You usually need at least 6 registers to store 1 bit, and then there's a whole bunch of circuitry around it. So you cannot, again, have a large SRAMs. The SRAMs is in order of kilobytes, hundreds of kilobytes at best, okay? Then you have another technology called DRAM, and DRAM is significantly more compact. It's only 1 register technically in order to store everything. But it's since you have less and less amount of registers to kind of drive this giant power, reading DRAM is incredibly slow, okay? Significantly slower than SRAM and register files, but it's very cheap. You can actually dense a lot of things. So you have order of gigabytes of DRAM in your systems. And lastly, you have what we call disk. So this could be either a flash or like older technologies like actual disk. These are very, very cheap. So you can actually store terabytes of data in like a small storage unit, but they are very, very slow in terms of reading them. They use a very, very different technology actually, but they're very, very slow. To give you numbers, again, register files are in order of few kilobytes. The access time is within 1 cycle. SRAMs in order of tens or hundreds of kilobytes. The access time is usually between 2 to 10 cycles, depending on the size. As the size grows, the access time also grows. Then we have DRAMs that are in order of gigabytes. So notice the kind of significant order of magnitude difference, but also notice the significant time difference. So as you can see, what used to be 2 to 5 now is 200 to 500. So 2 order of magnitude different. And then finally, you have this. And then again, another order of magnitude improvement, but also multiple order of magnitude, unfortunately, decrease in the access, right? So this is kind of the status quo, that you cannot have large and fast, okay? But you need large and fast, right? Because there are lots of workloads that require lots of data to be stored, and you cannot really afford to wait thousands of cycles to kind of read that data. So what should we do? And that's where the story of kind of memory hierarchy comes into play, okay? So the basic idea of hierarchy is, let's actually have different tiers of memory. And if I can move the data intelligently, and if I can bring the data closer to where I want, I can basically have this illusion, have this virtualization idea that I have a very large and very fast memory, okay? So let me give you an analogy that's that people usually use. The book is also used. So this is the library analogy. I think I gave you this before, but let me repeat this. So consider data as books, okay? So all the books in the world is the data that you want, right? And then of course you can store all of these into a public library, right? But accessing a public library is incredibly slow. So if you're sitting at your home and you want to read a book, you have to go out and drive and find the first public library, go inside, find the book. So this is like hours of access time. Versus if you had the book on your table, you basically instantly access the data, right? So you instantly pick up the book and read, right? So this is the difference. You want that instant access, but you cannot have all the books in the world on your desk, right? This is very intuitive and very basic. So how do we fix this? We basically use this idea of kind of frequently used or kind of memory hierarchy to kind of fix this issue. So what you do is that you're going to say that, okay, in my desk, I have the capacity of storing 3 books. I can stack 3 books on top of each other. So here's what I'm going to do. Instead of just randomly picking 3 books and put it here, I'm going to pick the most recently ones, the ones that I'm very, very likely to use in near future on my desk, right? If I have a midterm of M116, then I'll put the computer organization book in my desk. If there is no midterm coming up, then it's very unlikely that I'm going to read this book. So I'm going to put another book in my desk, right? So I'm going to put the frequently used books in my desk, but then I can also have other hierarchies, okay? So maybe I also have a shelf. Maybe also there is like an attic in my house, and so on and so forth. So not everything is either on my desk or in the library. There is also in between hierarchies that I can leverage, okay? So I can put it into the desk. I put it in the shelves, and then less rarely used, I'll put it in the garage or in the attic or in the box, and so on and so forth. So I actually create this kind of layer by layer memory hierarchy, which I'm going to put things that are less and less likely to be used further from me, right? So closer is to me is the data that I'm very likely to use. Farther away from me is the data that is very, very unlikely that I'm going to use. But I'm still access to everything. Still, if I need to use this very weird book, I can go to the library and bring it. So I have access to all things that I want. But on the average case, most of the time, I'm going to really read this just 3 books that I have on my desk. So on the average, I basically have the latency of instant reading the books on my desk. But in reality, I have access to everything that I want. Okay, this is kind of the magic of memory hierarchy. Okay, so let's the rest of this lecture is let's actually talk how we can achieve this and how we implement this. But the basic idea is just this. Okay, any questions? So why would this work? This worked because the idea of locality, and we kind of discussed this in BTBs as well. So as I said, there is a very, very likely chance that we're gonna use certain things in short period of time and in nearby data, okay? So if you remember, we had temporal and spatial locality. The reason that memory hierarchy is actually a good idea is because most of our programs experience various different types of localities, either temporal or spatial. So for example, the examples of the book and your midterm was the temporal locality, right? Another example would be like your M116 book and maybe your 111, like the dinosaur book that you have for operating system course. Probably you've taken these two courses at the same time in the same quarter. As a result, you have both of these books on the same desk, and then probably the midterms are also close to each other, right? So this is the idea of what we call spatial locality, that if there is a chance of I'm accessing this, there's also a very good chance that I'm going to access something very similar to this, right? Think about an array. If I access index 0, very likely I'm going to access index 1 and 2 and 3 and 4 in near future. So what I can do is that if I'm bringing 0, I can bring 1 and 2 and 3 with me so that the next time I need them, I have them ready. So this is the idea of locality, okay? So this is kind of like, just showing this again. So the idea of memory hierarchy is that I'm going to have very, very fast memory inside my CPU, but they are very, very small. And that is my register file. The register that I'm going to keep and continuously use, I'm going to put it very, very close to me. And me here is the CPU. Then I'm going to have like an SRAM here, very, very small, but very, very fast. And then I'm going to kind of go and grow the size of my memory. But as I move toward this direction, it gets slower and slower. But if most of the time I'm really just using the data within my register file, or I'm just using the data within my M1, although that I have access to everything, I really see only the latency of my M1 and my register file, right? So that's how we fix the issue of memory wall, okay? So what is this M1, M2, M3, and so on? For now, we're gonna basically start with the simplified design, and we're gonna have basically a kind of a 4-tier memory hierarchy system. So we're gonna have the register files inside my CPU. That's kind of like my level 0. Then this thing that is kind of sits near the CPU, we call this a cache, okay? And the cache could be either a data cache or instruction cache, or it could be a combined thing. So I can distinguish between data and instruction, or I can have the same thing. And then I'm going to have what we call the main memory, which is the DRAM. And then I'm going to have my disk, okay? And then in terms of view, this is basically the same thing most of the time. And then so basically I have my CPU, I have my cache, and I have my main memory. That's it, okay? Kind of like these 3 things. That's all I'm going to have. Later on, I'm going to add a little bit more details to every step. But for now, just consider that this is kind of like what we have in a typical memory hierarchy. I have CPU, I have cache, and I have main memory. Okay. And then within this cache, I might have multiple layers or levels. We call them L1, L2, L3, L4, and so on and so forth. For now, let's assume that there's just one layer and we call that level 1. But in future, we're going to add more layers to this as well. Okay. So let's have a quick break and we come back and then we're going to talk about this this cache and memory hierarchy. All right. Let's continue. Don't forget about your homework. It's on Thursday. It's on basically just one big example of out of order execution. And then there's also another for BTBs. The project's going to be about caches. So I'm actually going to release it probably this week sometime. And your next quiz is also coming soon, right? So it's going to be about out of order execution and part of the cache, okay? And I think the quiz 1 grading is almost done. It's going to be released within a few days, hopefully by this end of this week. Okay? Any questions? Yeah.
For the homeworks, do you want us to split up the cycles as like an bit or each was separately on the entire big issue and like highlight each of the differences, or you might work condensed where everything is
The question is for the homeworks, do we want to kind of split the different cycles in different slides or one dense? Since we are not really going through the correctness, you can submit any. But in the exam, you probably want to do different ones so that you can get partial grading. I mean, you have to do it anyway if you're really solving this, right? So you have to keep track of every cycle. So my suggestion is just create like a slide deck and then kind of go through them cycle by cycle and then just submit that as a one PDF.
Oh, my question was like, do you split up the cycles too? Because there's like.
Oh, the split the cycles itself. Yeah, that could be one cycle if you can keep track of things.
Okay.
Yeah, that should be fine. Yeah, if you can actually see my slides, it's also the first is kind of like one step at a time, but then afterwards it's just big steps, right? So there was also last year, I think, there was lots of there were lots of people with papers that wanted to answer it and they couldn't like have the slides. So there was like all these problems of, oh, what should we do? And we cannot have the slides in the quiz. So we kind of find another way of them to write it down. So yeah. All right, so let's talk about cache design. The first thing that you need to know is the notion of hit and miss. We kind of also talk about this a little bit, but generally, if the data is inside the cache, we call it a cache hit. If the data is not in the cache, we call it a cache miss. Obviously, you want to have a very, very high hit rate because you want to have all your data stored in the cache. If it's not in the cache, it means that it's in the main memory, so you kind of incur some overhead, right? So you want to have as close as 100% accuracy, 100% hit rate on your caches. Of course, you can never mathematically reach 200 because there will be some data that is not going to be in the cache because the size of the cache is smaller than the size of the memory. It's mathematically impossible to have everything in the cache, right? But you want to have 99.999 so on % hit rate. If you can achieve that, that's the ideal scenario. So why caches are important for the performance? Let's actually talk about this. So if you remember, we kind of talk about this data memory kind of very casually in our pipeline stages, whether in order or out of order. And then we always say that, okay, access to the memory, one cycle, and that's it, right? In reality, that's not true though, because memory itself is a very complex, design. As I said, if it's within the first layer of your cache, then yes, that's one cycle. But if you actually go to the main memory, that's hundreds of cycles, okay? So far, we didn't really talk about that, but now we should, in realistic scenario, we should talk about that. So to give you kind of like some numbers, just think about that this data that is not there, what will happen? It will result in stalling the processor, right? So how many cycles are we stalling? So if it's in the level 1 of my cache, it's going to be 1 cycle, so that's very quick. But if it's in other layers, we are talking about tens and hundreds of cycles stalling. And that's directly impact the performance of your CPU. So that's why memory is not a separate thing. The performance of your memory has a direct impact on your CPU. If your data is accessible as soon as possible, as fast as possible, then that will translate into your IPC or CPI, okay? So your performance actually increases. So everything is still about CPU time. What's really happening here is that if the data is not one cycle achievable, then we're going to incur stalling and then we're going to reduce the IPC, unfortunately, right? So that's why the memory delay is so important, okay? So now let's talk about how we actually design this. So basically the goal of the cache design, as I said, is the minimizing the amount of time accessing to the main memory, right? So minimizing stall. So all we talk about here is that how we can access the data that is stored in the memory as soon as possible so that we don't incur stalls. So in order to measure this, we're going to use this metric called average access time, okay? So this average access time is basically the average access time to read one data, 1 byte, or I don't know, 1 word, depending on how we define it, from the memory, okay? So what is this average access time? This average access time is basically a combination of 3 main things. The first one is the hit time. The second time is the miss rate, and the third one is miss penalty. So what are these things? The hit time is the time it takes to access one level of cache. Okay, so assuming that we are going with the simple design of having only CPU, cache, and main memory. If my pen works. Okay. Hopefully it works. Yes. All right. So if you have this design of CPU and then cache and then main memory, CPU, cache. So what will happen is that if the data goes to the cache and come back, we call that hit time. Okay, the time it takes to access the cache. And as I told you, usually this is one cycle. Okay. But of course, as I said, this is not always possible because the size of the cache is much smaller than the size of the memory. So there will be scenarios where the data is not in the cache. So we have to go to the main memory and bring it. Okay. So the average access time is the average between the times that data is inside the cache versus the time that data is not in the cache, right? So this is how we basically can calculate this, right? In both cases, we have the hit time, right? Plus, so this is just the time for the cache, and this part is the time for going to the main memory and coming back. How often do we go to the main memory? That's the miss rate, right? So if like 90% of the time I'm hitting the cache, that's the only time that I'm just using this hit time. If that 10 other percent of the time that I go to the memory, that would be 0.10 times the miss penalty. What is miss penalty? The time it takes to bring the data back from the main memory. Okay, so for example, if your miss penalty is 100 cycles, if your miss rate is 10%, and then if your hit time is 1 cycle, what we're going to have is that we're going to have 1 cycle all the time, because whether you have a miss or a hit, you always have to first check the cache. That's 1 cycle. Plus, you're going to have 10% of the time, you're going to have 100 cycles of miss, of accessing, right? So on the average, what you're going to have is that you have around 11 cycles. On average, this cache, this whole main memory plus cache, has 11 cycle latency. And then if you, for example, change this 10 to 5, right? Which means that 95% of the time now I'm hitting the cache, then of course this number will shrink down. So this would be 0.05, and then this becomes 6, right? So, you know, just simple math. Yeah.
Why are L2 and L3 not considered?
So the question is why L2 and L3 is not considered. Again, so here I'm just assuming there's one layer of cache. Very simple. Later on, you're going to see what happens if I add more. And then actually this will be slightly updated, but in principle, this is just a very simple formula. Yeah.
And just a quick question, the average time is in cycles, right? It's in cycles.
Yes, this is in cycles.
Why is the average time not a weighted average? So, if we're multiplying the rate for units of time, why are we multiplying the hit rate by that?
So the question is why there is no 1 minus miss rate here, right? And there is actually, so it's an the reason this is like this is because of this. So in reality, you have 1 minus miss rate, okay, times your hit time plus miss rate times miss time, okay? But then the trick is this miss time itself is equal to hit time plus miss penalty, okay? Why? Because imagine a scenario where you go to the cache, you always first check the cache, so you always pays the hit time penalty, If it's not in the cache, you have to go one layer down and check your main memory. So that's why your miss time is the time for checking the cache and checking the memory. Checking the cache, we call it hit time. Checking the memory, we call it miss penalty. So if you actually do the math, you will see that's kind of these things cancel each other out. That's why you just end up with hit time. Okay. So basically, you always pay the hit time penalty. Sometimes you pay the main memory penalty, sometimes you don't. That's why the miss rate is basically coming into it. Okay. So basically, what does this say? This say that there are three very important things. One is you want your cache itself to be very, very fast because this hit time is basically always there. So you cannot really afford to have a slow cache, okay? So your hit time should be always 1 or ideally even less than 1, okay? Another thing that you want to have is that you want to have as less as miss penalty as possible, right? Sorry, as less as miss rate as possible. The lower the miss rate, the faster your system is going to be, right? And finally, if you can somehow reduce the miss penalty such that if in those rare cases, you just quickly can grab the data back, you're again going to have faster system. But among these three, miss penalty, I would say less important than the other two. Hit time, of course, is the most important metric here because it's always there, right? So, I mean, we're going to talk actually about how we optimize each of these three. Let's first talk about the structure of the cache in this lecture. In the next lecture, I'm going to come back to this hit time, hit rate, and miss penalty. And we're going to describe different techniques to optimize each one by one. Okay. All right, so let's continue. So this is the formula. So as I said, the idea is that we want to minimize the access time to cache. The problem is limited space. So let's first see how do we store and how do we structure the cache. And as I said, we're going to come back and talk about optimizations. So let's talk about the first thing that we can do. So first of all, how do we actually store the data into the cache? What are the options? How do we actually implement this in real hardware? So in order to answer that, of course, we have to ask this question of what do we have and what do we need, right? So what do we have is just an address. In our design, this is a 32-bit data. The address that's coming from the CPU. That's the input of our system. So if you consider memory as this black box, the input is basically this 32-bit value. The output to this would be the data that we want back into the CPU, right? Of course, when we are talking about the cache, so for our memory, miss or hit doesn't matter. So you cannot have not data in your memory. You always have the data in the memory. But since the cache is only a subset of memory, there might be a scenario where you're going to have a cache miss. So for your cache, you really need to know whether your data exists in the cache or not. So in the ideal scenario, as I said, if I have all the lines for the address that I have, in other words, if I have 4 billion lines, then I won't have a miss, right? Because I have 2 to the power of 32 different addresses. If I have 2 to the power of 32 different lines, there is a one-to-one mapping between addresses and my memory content. In other words, I'm not going to have any sort of cache miss, okay? But that requires 4 billion lines or 4 gigabytes of data, which is not possible, okay? So what we have instead is that, since we don't have all the lines in my cache, there are scenarios where the address comes, but we haven't stored that data into my cache, okay? So how do we actually store that data and how do we find where that data is? So this is basically the reality. If you consider this as your cache, let's say it has 8 different rows. I'm showing the rows like this. And then if this is your main memory, and let's say your main memory has 32 different rows, so you have a 5-bit data, so everything is inside your main memory, but only 8 of them is inside your cache. what will happen is that, of course, there will be multiple different rows in your main memory that will be mapped into the same row in your cache. So for example, the graph that I'm showing you here, all these gray kind of lines are mapped into this one gray line here in the cache. So basically each 4 is mapped into 1. So you have a 4-to-1 mapping between main memory and your cache. And then this happens for all the lines. So for all these blue ones are also mapped. And now, of course, the question becomes, how do we do this mapping, right? So what's the best way of doing this mapping in order to achieve the best type of performance that we can have, right? So basically, I'm going to answer these 2 questions. First one is that, first of all, how do we know which of these 4 blue lines are actually stored here? Because technically there is a 4-to-1 mapping. So this line could be any of these 4 lines. So we need a method to kind of know which one is which. And if you remember, this was the same issue that we had with BTBs. And there we introduced the notion of tags. We're going to do the same in the caches as well. And the second question is, what mapping should we use at all, right? So what's the reason that I kind of map these 4 into this line? Why I'm not mapping this one and this one and this one and this one to this line, right? So there are a whole bunch of different mappings. There's a 4-to-1 mapping. I can just basically pick any sort of mapping for this. It should be deterministic, but it should be anything that I want, all right? So basically, to answer this first question, as I said, we're going to use the same technique that we use for BTBs. So we're going to use this idea of tag in order to know what we have stored. And then if there is a match between the tags, then that's where we're going to basically read the data, okay? So the tag is just there to tell us what we have stored, which of these 4 lines. So let's say I assign different tags for each different one. So let's say, for example, this one is 0, this one is 1, this one is 2, and this one is 3, okay? So basically, in each of these, I'm going to store the tag here, and then I'm going to store the data here, okay? So now I want to read it. I first check tag, see which one I've stored. If the tag is matched, it means that I have stored it in the cache. If the tag is not matched, it means that I need to go to the main memory and bring that data to the cache, right? And then why do we have this reason? Why do we have this problem again? Because the size of my cache is much, much smaller than size of my main memory. So I cannot store everything, right? So that's what we're going to have. So what do we store as a tag? Let's give you a very, very simple example. Let's say we have only 3-bit address. I'm just doing a very simple thing. So if I have 3-bit address, I have 8 different possibilities, right? So I'm showing the addresses 000 to 111. And let's say I have A, B to H here, okay? In my main memory, I have this 1-to-1 map. For every address, I have 1 data available. And that's great. So there is no notion of miss in memory, right? But in the cache, let's say, for example, my cache is only for 4 entry, okay? So in cache, I have addresses 00, 01, 10, and 11. So there will be a 2-to-1 mapping between my main memory and my cache. So how do we actually store this? The simplest thing that we can do is that think about that the lower addresses can be used as the index. So basically this blue part is the same as this index. So this 00 is here. This other 00 is also here. So I'm basically kind of saying that, okay, these 2 lines are mapped into this line. Then, and then maybe then this 2 and this 2 is mapped into this line, and so on and so forth, right? So essentially, based on the similarity of the index bits, I'm going to map things to the cache, okay? And now the question becomes, what should I store as a tag? Since I already used these 2 bits, the only thing I need to store is the remaining bits. So in this case, it's just 1 bit. So basically, in my tag store, I only save 0 or 1, right? Just 1 bit, because I already used these 2 bits. The only thing that remains is just whatever remains. So if this was 4, I had to store 2 bits. If this was 5, I had to store 3 bits, and so on and so forth, right? We kind of discussed this in the BTB as well. So the mapping would be based on the similarity of index bits, and the store data that we store in the tag would be whatever remains from the address. Okay, so that's how we're gonna basically map this main memory to my cache. And this is only one mapping for now. I'm gonna actually describe other mappings as well. Okay, and of course, I still need to store the data. This is just for knowing which address I have saved. Okay, so this is what we call a tag store. I still need to store the actual data. In this case, my actual data is this A, B, C, D, E, F, G. So I still need to store either A or E, depending on whether I'm storing this one or this one here, or I need to store B or F, whether I'm storing this one or this one. So I have two kind of storage units. I have the tag store to store what I have in the, to kind of indicate what I have stored in the memory or in the cache. And then I actually need the actual data as well. So two things that needs to be stored, okay? So this is kind of like, you know, the idea for this part, that what we are storing really in the system. But then there's question of what mapping should be used, okay? And there might be different mappings that come to the mind. And then the question is which one is better and why, and which one should be used. Any suggestions of what sort of mapping should be used? I already gave you one. What was that? Any suggestions?
Well, you just use the lower bits. But
Yeah.
I think I would suggest that you do something such that, that like places the spatial quality so that, basically instead of basically it needs to like look up.
So we kind of use kind of like some form of like lower bits and say, okay, this lower bits just goes to this line, this lower bits goes to another one. So some form of what we call a direct mapping, that we map the particular addresses always goes to the one line, right? And then we can choose how do we do the mapping. Maybe we can use spatial locality a little bit better and so on and so forth. That's true. And any other suggestions? Something that's completely different than this. There's also another intuitive way. Yeah. Yeah.
So, use why do we even need to do the mapping? Because before, at least, the other strategies we done table. So why can't we also do like some sort of table design of cache?
Well, what is the table design for cache? Like, can you explain?
So in this case, we're trying to map a larger set of memory to a subset of memory. Why don't we do the mapping? Just say, order like if we like have a
so the question or some form of comments is that why don't we use some form of key? But the key is also the same as mapping, right? So you can either use the address or you can use some form of a hash, but they're all the same, right? The address comes, you make a decision, you create a key or whatever, and then you go to one line, right? You have to know where you have stored things, right? You need that in order to know what you have stored. But how do you do that mapping is the question. Any suggestion? Yeah. You can index the rows. Yeah, so you can use different ways of hashing, and that's true. But there is other very different ways of storing this. Any suggestions? Come on. Nobody? So the first one is, as I said, you can organize this into one line specific. And as I said, this is what we call a direct map design, okay? So the direct map design is that I'm going to use some form of mapping. So I'm going to get the address. I'm going to use some form of mapping and say, okay, this one has to go to line 1 or it has to go to line 2, right? And I can be creative with that mapping. I can just use the lower address. I can do hashing, whatever. But the other way that I can do this is that think about the cache as just one big storage unit with multiple rows. Okay, let's say I have 4 rows. And then what I'm going to do is that instead of saying that, okay, address 000, for example, comes, this one has to be stored here. I'm going to say that basically first come, first serve type of scenario. I'm going to store things in the whatever available row that there is. Whatever there is, I'm going to store it there. And then the next one that comes, I'm going to store it to another space available. And then in order to search, I always search through the entire table, right? So if the new address comes, I basically just go through the entire thing and say, where did I store this? The good thing about this, obviously, is that you're using this space as efficient as possible, because you guarantee that there is no available space until the entire table gets fully, full. Versus if I just do some form of mapping, if there is an address sequence that's kind of like all mapping to the same line, you're kind of kicking each other's out without really utilizing the rest of your table, right? So there's kind of these kind of two trade-off between the design. The first one, we call it fully associative, that you kind of fully use your table. And the second one, we call it direct map. So let's talk about these two and see what are the differences, pros and cons for each of these two designs. Okay, so the one that the same index goes into the same row, we call that direct map. The simplest things to do is that using the lower bits. Okay, so for example, if this one has 3 bits, I'm going to use the lower 3 bits here to map this. So if you can actually pay attention to this gray one, you see that all that has 001 in the right side of their address, they all map into this 001 here. And then if you look at the blue ones, you see that those that are 101, they all go to this 101. Okay, so I'm using the lower 3 bits and basically just indexing directly here. But the problem with this approach is that if, for example, my access pattern is this, and this, the way that I'm going to store this in the cache is that this one first goes and stored in the cache. Then this one comes and kick this one out and then replace itself with that. And then this one comes and this one comes, while the rest of my cache is completely empty. Versus if I just do the full table, I can say, okay, the first one comes, go to the first row. I don't care about the index or address or anything. Just go to whatever available. Just go and sit on the first seat that you see in this room. And that's basically the idea of fully associative. The problem with this approach is that it's very hard to find this, right? For this direct map, I exactly know where this is stored. But for fully associative, I have no idea where this is stored because it could be anywhere in my cache, right? So that's kind of the pros and cons with these two approaches. So for as I said, for direct map, this is basically how do we do this, right? So we break down the address into an index part and into a tag part. I already discussed why we need 1 bit. So basically in this case, I have 2 bits of index and 1 bit of tag, right? So my tag store is only 4 by 1, right? So 4 by 1 is my tag store. And then how do we do the lookup? So basically, if you remember, I told you that I have tag store and data store. The way this works is that my index will basically pick the right row first. Then we're going to check the tag. If the tag matches, we call it a hit. And then we read the data from the same row. Okay. If the data is not there, this is a miss. So this data it's not valid. You have to go to the main memory and bring that data from my main memory, right? So index for selecting the row, checking the tag to make sure that this is the correct address. If it's the correct address, then we read the same row from my data store, okay? And then one optimization that we do is that we access the tag store and data store at the same time. We access them in parallel, okay? So basically what we do is that as we read the tag, we read the data too. Once we know that the tag is valid, then we're going to pass the data in. So this is kind of like the MUX idea that we also had in my PTB. So you don't do checking the tag first and then reading the data because that makes it serialized. You have to check the tag first and then the data. What you do is that you bring them both. You then check the tag. If the tag is good, then you let the data go. Okay? So that's the optimization that we make. But the alternative to the direct map is, as I said, is what we call fully associative. In the fully associative, the entire address becomes a tag because you don't no longer have the notion of index, okay? So basically what you do is that any of these addresses could be stored anywhere, okay? So I no longer respect the index, but as a penalty that for this approach is that now I need to store the entire tag, okay? So this was direct map, and this is what we call fully associative. Basically, I need to store all 3 bits as my tag because I no longer use the index to kind of tell me which one is which. So if my address is 32 bits, I need to store the entire 32 bits as my tag, okay? And I'm still gonna store the data the way that it was, so ABC, but as you can see, my tag store becomes significantly larger because it used to be only 1 bit, now it's 4 by 3. So it used to be 4 by 1, now it's 4 by 3, okay? But the benefit of this is that now I'm storing 4 things and they don't necessarily competing with each other. If there is more space, then I can store more things, okay? Let me give you this example very quickly, and then we're gonna call it a day for today. So let's say, for example, we have 8-bit addresses and we have 8 rows, okay? And then let's say we have a direct map cache and a fully associative cache, okay? Let's see what happens in terms of storing the data here, okay? So first of all, the tag size for each of these. What would be the tag size for the direct map? Any suggestions? What would be the tag size for the direct map? We have 8 rows in my tag, so 3 bits address for index. What would be the tag size? Yeah, what's that? 5 bits, right? So we have 8-bit address. 3 of it is used for index, so I need to store 5-bit addresses here, right? 5-bit for the tag because I'm already using 3 of it. Remember, I'm just giving you an example of 8-bit. In reality, this is 32. So if I do 32 minus 3, that would be 29. But in this particular example, I'm just using 8 bits. And what would be the tag size for the fully associative? 8, right? Because I need to store everything, right? So that's one thing to remember. Then let's say, for example, I have an access pattern like this, 0, 1, 2, 8, okay? So how does these two maps into my direct map and my fully associative? So for example, let's say my cache starts empty in both cases. So the 0 comes. So the 0, so basically the way that you need to do this is that you need to convert this into 8-bit binaries, okay? And then you need to check the first 3 bits. And that's where you're going to decide which index this goes, okay? So for example, for 0, 0, this goes here. The 0, 0 tag for 0, 0 is the other 5 bits, which would be 0. And of course, the data would be something here, okay? And the valid bit becomes 1. For direct map, for fully associative, I don't care about the index. I just find the first available spot. So I put 0 here, okay? Then I put 1 here, basically the next address. The index for 1 is something like this, right? So the index in this case is here. And then if you look at the tag for this one is also 0, 0, 0, 0, right? Because the upper 5 bits are the same. So I basically, again, store 0 here, put valid here. But here the tag is actually 1. The tag is different, right? So valid here, 1, 1. Then 2 comes, and then 2 basically goes here. Again, 0 here, valid here, 2 here, 1 here, right? I'm just showing it in decimal, but you can show it in the binary or hex as well, okay? Then the interesting thing comes when this 8 comes. And if you actually write 8s in binary, it would be something like this, okay? So what happens here is that the index is actually telling you that this is 0, okay? I go to 0 and see that I store data already here, but tag 0. But for 8, the tag is actually equal to 1, right? Because this first bit of the next 5 bits is 1. So I need to kick this out and replace it with another data that's tag is equal to 1. For fully associative, though, I don't need to kick anything out. I just put 8 here, okay? So that's the difference fundamentally between direct map and fully associative, that in fully associative, you kind of utilize your space a little bit better, okay? So this, in all of these cases, these are all missed because my cache is empty. But if I repeat this, you will see that it's actually at some point you get some hits. Yeah.
Why are the tags all zero for direct
Why tags are all zeros? Because if I put 0 in 8 bits, it would be something like this. So I pick the first three, and then this 5 bits would be my tag. So this is equal to 0, right? And then if I do it for 1, it would be something like this. Right? And then again, this would be my index, this would be my tag. So my tag is still 0. So you have to write it in 8-bit format, pick the 5 bits, that would be your tag. If the addresses are 0 to 8, yes, but for 8, for example, so 8 is like this, right? So in this case, the upper 5 bit is 1001, so your tag is equal to 1. Right? So for example, you had 16, that would be 2, or so on and so forth. It's just a binary manipulation. And then finally, if I look into this example, but with a different addressing, you will see that if I have something like this, if I have 08080808, if I have a repeating pattern of 0 and 8, in direct map, what will happen is that you first write 0 here, then 8 comes, and if you remember, 8 tag was equal to 0. I have to kick out 0 and put 1. And then 0 comes again, and then I have to kick out 1 and put back 0. 8 comes, I have to kick out 0 and put 1. So basically, they kick each other out alternatively. Versus for fully associative, I had 0 here, I have 1, sorry, I had 8 here. And the next time that 0 comes, I already have the data, so that would be a hit. Okay. So essentially, for fully associative, the pattern that I'm going to see is miss, miss, and then hit, 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 hit. So the first 2 are going to be miss, but the next 4 will be all hits. Versus for direct map, all of them going to be misses. Because I'm storing 0, I need 8. I'm storing 8, I need 0. I'm storing 8, storing 0, I need 8. So it's kind of like alternatively changed. Okay. So yeah, so that's the difference between direct map and fully associative. So that's where we're going to stop here. We're going to come back and talk about difference in terms of miss rate, miss penalty, and hit time for each of these two. And then we're going to explain another alternative, which is what we call set associative.